Okay, let's go ahead and get started. So just administrative announcement. It was pointed out to me that the last problem on the problem set is actually one I already assigned. I'm sorry. I actually knew that I'd assigned the later parts of that problem, but I'd somehow thought that I hadn't decided to assign the earlier part. You can do the last problem on your problem set if you like. If you don't remember what the answer was from when you did it at the beginning of the semester, but you don't have to. Okay, it's up to you. Also, there's a mysterious factor of a half floating around. I think in that problem where I had a separate phi and a chi field, I accidentally put in a factor of 1/2 twice. That's sort of obvious. You can keep that factor in if you want. You don't have to keep it. It really doesn't matter to me. It might matter to Scott because he'll have to figure out when he's grading the problem set. But that's his problem. Okay. So what I'd like to do is go ahead and continue with our discussion of gauge theories. So in particular, last time we discussed the quantization of electromagnetism. And at the end of the class, I began to articulate really what is going to be one of our central tools in our construction of quantum field theories, which is known as the gauge principle. Okay. So what I'd like to do today is just talk in a little bit more detail about the quantization of electromagnetism. And in particular, what I'd like to do is begin with sort of a review of some of the things we discussed at the end of the class last time, but with an eye towards understanding a little bit more generally what the structure is of these theories that we are going to be constructing. Okay. So the gauge principle is a very general strategy for constructing interesting interacting quantum field theories. And in particular, it appears to be the principle that underlies all of the quantum field theories that are responsible for the fundamental forces of nature. Okay. And the basic way that the gauge principle works is the following. Okay. So what you do is you imagine that you have some sort of theory, a quantum field theory, which has a symmetry that I will refer to, for reasons that become clear in a few minutes, as a global symmetry that is parameterized by a continuous parameter that I'll call lambda, which is the analog of the gauge parameter that we introduced last class. So we imagine starting with some theory that has a continuous symmetry. What does that mean? That means that there is some transformation where you start with some field phi that depends on where you are in space-time, and you make some transformation to some new field that now depends on your continuous symmetry parameter lambda. And this transformation will be a symmetry in the sense that the equations of motion will be unchanged. So that when you write the equations of motion in terms of this new field, phi that depends on lambda and x, the equations of motion will be independent of lambda. And you imagine starting with a theory with some sort of global symmetry, and then you promote this to a local symmetry by coupling to some sort of gauge field. So you couple phi to a gauge field. And then there is going to be some sort of new force associated with this gauge symmetry. So a new force associated with this gauge field. Okay. So the prototypical example, and the only example of this that we'll be studying, at least in the near future in this course, is the example of charged fields coupling to electromagnetism. So in this case, you have a field phi which is a complex scalar, whose equations of motion are given by the Lagrangian, which is just the natural Lagrangian of a real scalar field, generalized in the obvious way if phi is complex, consistent with the principle that the Lagrangian has to be real. And then we note that this is invariant under the global symmetry, where phi goes to e to the I lambda times phi. Okay. And I put a little minus sign there. That's just some convention. You could always take lambda to minus lambda. Okay. So this is an invariance of the theory, a symmetry of the theory when lambda is a constant. But then the idea is that we introduce a gauge field, a mu, which in the case of a charged scalar field will be the vector potential of electromagnetism. And then we let the symmetry parameter lambda be a function of position in space, whereas previously it was just a constant that was the same everywhere in space-time. And then we demand that our theory is invariant under the gauge transformation, where phi transforms as it did above, but now with lambda some function of x. And A will have to transform in some way to compensate for the fact that lambda is now a function of x. And then what we saw last time is that although the original Lagrangian up here of the charged scalar field is not invariant under this new symmetry where lambda is a function of x, there's a very simple modification of it which will make it invariant when lambda is a function of x. In particular, if you replace the usual derivative d mu appearing here with a covariant derivative, typically denoted by capital D mu, that will be invariant when lambda is an arbitrary function of x, where the covariant derivative is defined as the usual derivative plus a correction term that couples a to phi. And we saw explicitly last term that indeed under a gauge transformation, d mu phi transforms exactly like phi does. So it goes like e to the minus I lambda of x d mu phi, so that when you take the absolute value squared to write this new Lagrangian, that guy is going to be invariant under the symmetry. Okay. The point being that this covariant derivative is going to be invariant under this gauge transformation because there's an extra term involving the derivative of lambda coming from the gauge transformation of that first term, which cancels the gauge transformation of a mu coming from here. And there has to be a relative minus sign somewhere in the game, which I've taken to be this minus sign up here. That's just a convention. Okay. I could have also changed the sign there instead. Okay. So just to make contact a little bit more closely with some physics that we already know, I'd like to introduce one more convention that we use when we talk about gauge symmetries. So in particular, phi is supposed to describe, is the field whose quantization will give you charged particles. And in particular, we'll be most interested in this class in the electron. So typically what we do is we introduce a factor of the charge of the electron, E, in this gauge parameter, and then we take phi not to go to e to the minus I lambda phi, but e to the I q lambda phi, and the gauge covariant derivative to be defined with an additional minus sign and a factor of e. So here, E is the charge of the electron. So it's the fundamental unit of charge. And Q is an integer, which basically tells you the number of units of the charge of the field phi, or the charge of the particles associated to the field phi, measured in units of the basic quantum of electric charge E. Okay. So, for example, if you want to describe an electron, as we typically will do in this class, then you would set Q equals to -1. And then the covariant derivative will be d mu A plus I E A mu phi. Okay. You can see here all that I've done is introduce a factor of E, which is the electric charge, along with a separate factor of Q, which is the number of units of charge, the amount of charge measured in units of E. And I've done this because there are certainly cases where we might want to describe multiple charged fields. Okay. You might want to describe an electron and a proton, okay, one of which has charge -1, another of which has charge +1. Okay. And so then you would describe, then you can see from this that those two fields, the covariant derivative of the electron field as opposed to the proton field would be different. One of them would have a plus IE A mu phi, the other would have a minus IE A mu phi. Now, life is going to get a little bit more complicated when we take into account the fact that protons and electrons all have spin, but at least the basic principle hopefully is clear here for the case of the scalar field, and we'll have to generalize this a little bit when we talk about particles with spin. There's one other very nice thing that is made clear by this convention, which is that the coupling constant of the theory, the thing that plays the role of G in the G over 3 factorial phi cubed theory that we were considering earlier, is the electric charge E. Okay. So E is the coupling constant. So, for example, if E is equal to 0, then you just have a free theory. There is no coupling between electromagnetism and the field phi. And if E is small, then you have a weakly coupled theory. Okay? And the method of Feynman diagrams that we use to evaluate scattering amplitudes perturbatively will be a very good approximation. Okay? And indeed, if you go ahead and work it all out for electromagnetism, then it turns out that E is actually about a third. This is the electric charge in dimensionless units using h bar and c equals to 1. Okay. So you might think that doing so that means that when you compute Feynman diagrams, you'll get factors of E appearing there. Higher and higher order Feynman diagrams will be suppressed by factors by more and more powers of E. A third is less than 1, so that seems like it's going to be a pretty good approximation. Now, a third is actually, I'll tell you a secret, not so much less than 1. So you might think that because of this, the perturbative expansion in quantum electrodynamics is not going to be very good. Okay. It turns out that the actual expansion parameter in quantum electrodynamics is not E, but rather E squared over 4 pi. So it turns out, so for example, when you compute, say, scattering amplitudes in quantum electrodynamics, contributions to 4-point functions, propagators, and so forth coming from Feynman diagrams, you'll always have two factors of E. Roughly speaking, that's because, for example, if you wanted to compute a photon propagator, a photon would split into an electron and a positron, and then they would have to recombine to give you a photon again. If you wanted a contribution to the photon propagator, that'll give you an E squared. And there are always the factors of 4 pi floating around. It just turns out that it's E squared over 4 pi that is the correct, I don't want to say correct, but that is a more correct perturbative expansion coefficient in the theory. And this guy is known as the fine structure constant. It's about 1 over 137. That is pretty small. Okay. So actually, when one computes Feynman diagrams in quantum electrodynamics, one's computing an expansion in this small parameter E, E squared over 4 pi, which is a little less than 1%. Okay. So that means that you can get to quite high degree of accuracy only computing one loop or perhaps 2 loop corrections. Okay. Good. Yeah. Any questions on this so far? Yes.
Not a question, just an annoying pointing out typos. In a couple places you have B nu implies equals partial mu of A plus.
Oh, I'm sorry. God. Sorry about that. Thank you. Good. Yeah, you should really point these mistakes out when I make them, not 10 minutes later, please. Thank you. Because then it confuses people somewhat less. But yes, thank you. Sorry about that. Did I make that mistake more? Okay, good. Okay, other questions, comments, concerns, thoughts, feelings? Okay, good. Let's see, where's it? Okay. So, maybe I should just take one more minute to talk a little bit about the idea underlying the gauge principle. So, the idea underlying the gauge principle is that if you have a field with a global symmetry, that is to say, you have some transformation where phi goes to e to the minus I lambda phi. That's a symmetry, and so it doesn't change any physics. And so in particular, the parameter lambda is completely unobservable. But you can now, in a setup where you have a global symmetry, lambda is the same everywhere in space. It's the same here as it is in Alpha Centauri. But I should be able, but just because of causality, I should be able to choose different values of lambda here and in Alpha Centauri. And so the question is, how can we, because lambda is unobservable, we should be able to promote lambda to some function of x just by causality. An experimenter off an Alpha Centauri would have no way of determining that his value of lambda that he's chosen to describe physics there is the same or different from my value of lambda here. Okay. And then the question is, how can we consistently write down a theory where that is true? Well, you are naturally led to gauge theory. And the remarkable fact is that all of the known forces of nature arise in this way. So in particular, the standard model of particle physics is simply a theory just like electromagnetism, but it's one where the gauge symmetry is somewhat more sophisticated. So in particular, the standard model includes electromagnetism. So we called electromagnetism a U1 gauge theory. But in the standard model, this is generalized somewhat. The generalization of electromagnetism is known as Yang-Mills theory. Yang-Mills theory is the gauge theory where you have more complicated sets of symmetries. And those symmetries are associated to groups, just like U1 is a group. SU2 is the gauge symmetry associated with what's known as the weak nuclear force. SU3, the strong nuclear force. And these are gauge theories. But they're gauge theories not of the simple transformations of a single complex scalar field that we wrote above, but of more complicated global symmetries, which schematically are of the form phi goes to e to the minus I lambda phi. But instead, phi here is not just a single field, but rather a vector or worth of fields. And lambda here is now a matrix. And the mathematics associated with these more complicated gauge theories is really not particularly complicated. There are just a few more indices to keep track of, and you have to keep track of the fact that the U1 matrices, that is to say numbers, commute with one another, whereas SU2 matrices do not. So there's a little bit more mathematics to take care of because of that. But the basic idea is the same, that you have some global symmetry. In the case, for example, of SO3, it's the color symmetry. You have three different quarks of three different kinds of color, and one can rotate among them using a 3x3 unitary matrix. And then you can promote that to a local symmetry, just as we did for electromagnetism, and that immediately gives you the interactions of the strong nuclear force. What's somewhat more interesting is that, well, I don't know if more, I shouldn't make value judgments here. What is equally interesting is the fact that gravity, that is to say general relativity, can also be understood as a gauge theory. But it's the gauge theory that arises when we promote the Poincare symmetries, that is to say translations and Lorentz transformations, to local symmetries. So, for example, the simplest sort of Poincare transformation is just a translation. So you could imagine a shift of your coordinates x mu. So that's a symmetry. So if you take x mu to x mu plus a mu, where a mu is some set of four constants, then phi goes to, then phi of x goes to phi of x plus a, which you could then, if you wanted to, Taylor expand when a is small. And you could think about this as a symmetry, much like the rotation of the scalar, complex scalar field, phi goes to e to the minus I lambda phi, that you would then promote to a gauge symmetry. Okay. In particular, if you allow a mu now to be a function of x, then the usual partial derivative is no longer invariant under that symmetry. Instead, there's a new kind of derivative, known not coincidentally as the covariant derivative, now the covariant derivative of general relativity, which is invariant under that symmetry. Okay. So to make a mu into a local symmetry, to promote the theory, to promote the shift symmetry to a local symmetry, where this constant a mu is now allowed to be a function of space, we need to promote all of our partial derivatives to what are known as they're still called covariant derivatives. I guess we would call them metric covariant derivatives instead of gauge covariant derivatives. They're usually denoted with a nabla symbol. I guess that's what you call it, instead of with the capital D. Now, general relativity is not something that we are going to study in this class too much, except maybe in passing. But I just want to mention that gravity can be understood in a very similar way
to the theories, the other gauge symmetries that we consider when we study the Standard Model. Okay. And just as there is a gauge field associated with the U1 symmetries of electromagnetism, which is the vector potential A mu, the gauge field of gravity is known as the metric. So it's now a 2-index object, G mu nu. And there's a sense in which the gauge covariant derivative grad mu of gravity is almost identical to this sort of gauge covariant derivative that we wrote down up here. And this analogy will be much sharper when we consider the more complicated gauge symmetries, such as the SU2 and SU3 symmetries that arise in the Standard Model. Okay. Yes?
Just a small technical point of it. Why is it the metric that's called the gauge field when it's the Christoffel symbols that play the same role in gravity that play the same role as the gauge field of the
Yeah, I mean, the reason, let's put it this way, the reason why it's derivatives of the metric that appear that don't appear in electromagnetism is really because you have a derivative right here, okay? So I don't want to, so, you know, you don't want to, you need to be careful on how you apply the analogy, because when I talk about the gauge theories of the Standard Model, for example, these are all gauge transformations where phi transforms linearly. That is to say, phi goes to something times phi. When we talk about gravity, it's a gauge symmetry where phi goes to phi plus a derivative of phi. So that means that the form of the covariant derivative is going to be somewhat different. And that's why in the covariant derivative of general relativity, you get things that are derivatives of the metric. It's really coming from this derivative right here. So, yeah, I mean, what I haven't given is the formula for the Christoffel connection for this this metric covariant derivative delta. I'm not going to, okay, because this is not a class on general relativity. I just want to point out that there's a sense in which this is one sort of complete unified structure. Okay, good. But the important point, there's one final important point to make, which is that so far I have talked about the matter sector, that is to say our fields phi, and how we couple them to the gauge field via these covariant derivatives. But we also need to have some sort of dynamics for the gauge field. Okay. And the dynamics for the gauge field really needs to be determined by some principle. And this is something that we'll be getting into in a great deal of detail later on in this course when we consider renormalization. And the basic point is that at long distances, the dynamics of the gauge field is determined by what's known as low energy effective field theory. So, in particular, if you know what the symmetry, the gauge symmetry principle is, then at long distances, you can determine, perhaps up to some undetermined constants describing the strengths of interactions in the theory, what the leading contribution to the dynamics, the leading dynamics of these gauge fields should be. Okay? At low energies, that is to say, at very long distances. Okay. So, for example, when you consider four-dimensional U1 gauge theories, then at long distances, at low energy, the leading term is just, well, is just the Einstein-Maxwell Lagrangian. Okay, that's what gives us Maxwell's equations. But for other sorts of symmetry principles in other settings, you might get other sorts of dynamics. Okay. So, for example, in 4 dimensions, if you have a theory of gravity, then the leading term is given by Einstein's equations. If, for example, you're interested in electrodynamics, not in 4 dimensions, but in 3 dimensions, let's say that you're studying a material which is confined to a plane, say graphene or something like that. That's a theory in 3 dimensions, 2 space, 1 time dimensions. And the leading theory is a theory not of electromagnetism, but a theory that's known as Chern-Simons theory. And in fact, this is the version of electromagnetism that you would want to use if you were studying a sort of a 3-dimensional material with charge-carrying excitations. And Chern-Simons theory can be used, for example, to study things like the quantum Hall effect, and it leads to all sorts of interesting topological properties of condensed matter systems. Hopefully this is something that we'll get to later on in this course. I'm not quite sure. But I really just want to make the point that just because the dynamics of the U1 gauge field that we know and love are Maxwell's equations, there's a whole wide world out there of possible dynamics for these gauge theories. And at leading order, at low energy, we have a general principle, that of effective field theory, that allows us to determine what the dynamics is. Okay. So all of this was a kind of general schematic overview, a sales pitch for gauge theories, why they're interesting and why they're useful. I think it's fair to say that the gauge principle is probably one of the most important and deep principles that has helped us formulate our understanding of fundamental physics over the last, say, 40 years. Maybe I should pause here. So what I'm going to do now, and what we're going to start doing today and continue doing next class and for some number of classes after that, is a more detailed study of the simplest gauge theory, scalar quantum electrodynamics. But before I do that, let me pause and see if there are any questions. No questions, really. Yes. Yes. Uh-huh. Yes, okay. So as you can see, if you have, let's put it this way. So here we have translations. There are 4 symmetries associated with their 4 translation symmetries. So you might think that there are 4 fields, 4 gauge fields associated with that. It turns out that there are, I guess the way that I should say it is, because translations, rotations, and boosts do not all commute with one another, the gauge fields associated with rotations and boosts are not independent of those associated with translations. Okay? So just to be a little bit more clear, you could imagine, so the gauge symmetry of electromagnetism comes because you have one continuous variable, lambda. You could imagine a time translation where you have one continuous variable, t0, the amount that you translate time by. Then you would expect a 4-component vector's worth of fields associated with that. Just like a mu is associated with the one U1 parameter of electromagnetism, you would expect there to be 4 fields associated with time translation symmetry. Another 4 associated with each of the spatial rotations, and that would give you a 4x4 matrix worth of gauge fields. And that's precisely what the metric G mu nu is. Okay. And so you might think that you have a total of 16 different fields. But, however, there are various symmetries that relate these. It turns out that G mu nu is a symmetric tensor, reducing you to 10 degrees of freedom. And it also turns out that, okay, I mean, this is not a class on general relativity, but it turns out that the various gauge symmetries associated with rotations, for example, are related to those associated with translations. One way that you can think about this is the following. There's actually a nice picture that you could draw. So let's say that you want to do, a rotation about this point, okay? Then you could think of it as a bunch of translations, okay? And if you've made translations local, then you're now allowed to do a different translation and a different direction at each point. So you can think of a rotation as assembling together a bunch of translations like this, once you've made the translations local. So maybe at least this picture can make it clear. I don't know. Does that look to you like a rotation around the point? It's supposed to. Okay. So this vector field I've drawn is supposed to be the one that rotates you around the origin here. The idea being that once the translations have become local symmetries, I'm allowed to have a different translation in a different direction at each point, and that immediately gives you a rotation. Good question. It's a nice picture. Glad I thought of it. Yes, questions?
Say you have two different field theories with two different gauge groups that have the same Lie algebra system, say SU2 and O3.
Yes.
Right. Then do they necessarily have the same interaction?
Good. It turns, that's an interesting question. At all orders so the question is whether the gauge, whether in the standard model, it matters whether this is SU2 versus SO3. Okay. It turns out that when you study Feynman diagrams and you work in perturbation theory, it does not matter. But if you consider so-called non-perturbative physics, effects that are not captured by Feynman diagrams, then it does matter. For example, there can be symmetry breaking effects that are invisible in perturbation theory, but are actual effects in the quantum field theory that would depend on the global structure of the gauge group. But as far as the Feynman rules that you would write down, those will only depend on the algebra, not on the group. Yes, good question.
The covariance derivative is the most general way to make the Lagrange invariance.
Most general way. I mean, it's certainly not the most general way. So, for example, I don't know. You could always replace your gauge covariant derivative by, I could always do that. F mu nu is gauge covariant. It doesn't depend on lambda because because of the equality of mixed partial derivatives, remember? So I could always do something like that, and I would still end up with something gauge covariant. So, but the terms that you get with this sort of simple minimal covariantization of the partial derivatives are going to be the leading terms that would be relevant in, at long distances or at low energy. Okay. But there's no principle that guarantees that this is the only thing that you have to do in order to make your global symmetries local. I mean, I think the idea is that you want to make your global symmetries local because of this causality argument. And then at leading order, this is the simplest way to do it. But in general, you should really allow in your Lagrangian all possible interaction terms that are consistent with your symmetry principles. Okay. I mean, this is the basic idea of quantum mechanics. All that is not forbidden is compulsory. So that all terms and all possible interactions that are not forbidden by symmetries should be there as interactions, including the ones where I added that f squared term in the covariant derivative. I'm not going to write it back in because it's sort of painful to look at. But yes, those terms could in principle be there. Good question. Yeah. I had something else I wanted to say. Okay, any other questions? Good. Okay, so this was all just a bit of an advertisement. So let's now go ahead and study the simplest gauge theory, which is scalar quantum electrodynamics. So again, the action is just that of a complex scalar field, where I've already made a mistake, where we covariantize the derivative, and you add this Maxwell term, which tells you about the kinetic term of the electromagnetic field. Where again, d mu phi is the partial derivative of phi. I guess should we set q equals to 1? Let's set q equals to 1. So it's the partial derivative of phi plus I e a mu times phi. Okay. And let's go ahead. What I'd like to do now is discuss the quantization of the theory and how we would go about computing things like scattering amplitudes using some appropriately modified Feynman rules. Okay. And again, as you can see, just schematically, you can already guess what the Feynman rules for this theory will involve. There's going to be some sort of propagator associated with the phi field, some sort of propagator associated with the photon, with A. There's going to be some sort of interaction term, and in fact, there'll be two sorts of interaction terms. So if you insert the definition of the covariant derivative into here, the leading term will be one where a photon splits into an electron and a positron. This will be proportional to E. And the next term will be one where you have two photons which collide together to form an electron-positron pair. And this will be proportional to E squared. And so what I'd like to do now is just use the knowledge that we developed in our study of scalar field theory to develop in a little bit more detail what these Feynman rules are, and then to start to use them to do some calculations. Okay. Any questions before I continue? Good. Okay. So when we study scalar QED, the first thing to remember is that if we think about the limit where the coupling constant E is very small, then we should be able to think about the theory as very close to a free theory. And in the free theory, the Hilbert space H describing the states of the theory is just a Fock space, just like in the theory of the real scalar field. Okay. It's just a slightly more complicated Fock space, where we have more than one type of raising and lowering operator, or creation and destruction operator, associated with the different sorts of fields that we have floating around. Okay. So, for example, to understand this Fock space, we just imagine taking the gauge field A and expanding in a basis of solutions to the equations of motion. So we saw last class that the solutions to the equations of motion are characterized by polarization vectors that I called epsilon. So here, I is an index that labels the two polarization vectors. P is the momentum of one of the modes in this Fourier expansion of A. The 4-vector P is defined in terms of the 3-vector P by P squared equals to 0. And we'll normalize these polarization vectors so that epsilon squared is equal to -1, because the polarizations are space-like. So for example, for a photon traveling in the z direction, the two linearly polarization vectors, the two polarization vectors in for linear polarizations would be in the x and the y direction. Yes, question. Oh, I'm sorry. Jesus Christ. Thank you. Thank you. And as in the case of the simple real scalar field, when we consider quantizing the theory, the expansion coefficients that I've called a sub p comma I then get promoted to operators in the theory. And they will obey the usual commutation relations of a harmonic oscillator. So there'll be a delta I prime and a three-dimensional delta function between p and p prime. And here HC over here stands for Hermitian conjugate. Okay. AP goes to AP dagger, epsilon goes to epsilon star, if you're using a complex set of polarization vectors, as you would, for example, for circularly polarized light. And then the choice of what actual polarization vectors you use is really a gauge choice. Okay. And so, for example, the simplest gauge choice of the epsilon i's is the one that we worked out last time in Coulomb gauge. So in that gauge, if you had, for example, a photon traveling in the z direction, then the two polarization vectors would describe either polarization, linearly polarized photons in either the x or the y direction. But, of course, you could always choose a different gauge or a different choice of polarization vectors. So that's the Hilbert space of the gauge field, the electromagnetic field. The Fock space is then built as the set of states where you start with a vacuum state that's annihilated by the A's, and you build up multi-particle states by acting on them with the A daggers. So, for example, A P1 dagger, A Q2 dagger, acting on the vacuum, would be some state where you have a photon with momentum P and polarization 1, and another photon with momentum Q and polarization 2. So this would be some sort of two-photon state. Good. We can now consider the Fock space associated with the field phi. So the only difference with our previous discussion is that now phi is not a real scalar field, but a complex scalar field. So again, what we want to do is expand phi in a basis of solutions to the equations of motion. And the equations of motion of a complex scalar field are exactly the same as the equations of motion of a real scalar field. Remember that a complex scalar field is just a linear combination of two real scalar fields. You could write phi as phi1 plus I phi2, and then as you checked, I believe on your first or second problem set, the equations of motion for phi1 and phi2 are just those for real scalar fields of the same mass, so that the full equation of motion is just grad squared plus m squared phi is equal to 0, just as it was for a real scalar field. That means that you can go ahead and expand in terms of some expansion coefficients that I've called A and B, just as you did for the real scalar field. The only difference now, and this is an important difference to remember, is that because phi is not real, when you quantize the theory and you promote these coefficients A and B to operators, they will no longer be Hermitian conjugates of one another. Okay. B is no longer equal to A dagger. Instead, if you wanted to work out the mode decomposition of the complex conjugate field, or the Hermitian conjugate field phi bar, that's the guy whose mode decomposition will be related to the original one by Hermitian conjugation. Now, everything that I've written here so far is correct, except that if you went ahead and you worked out the algebra of the operators A and B, you would actually find something slightly funny. Okay? So remember, the way that you would do this is you would find the canonically conjugate variable pi, which is the variable canonically conjugate to phi. You would use the canonical commutation relations. You know, the analog of the commutator of x and p being I h bar would then be the commutator of pi with phi being I h bar times a three-dimensional delta function. If you went ahead and plugged that all in and you worked out what the algebra was for the a's and b's, you would actually find that, as I've written it, the a's obey the harmonic oscillator algebra and the b's obey the harmonic oscillator algebra with the wrong sign. So the commutator of a and b would of b with b dagger would be -1 instead of +1. It's because I've chosen, for a sort of arbitrary convention, to put a plus sign here instead of a minus sign here. So that means that what I'll actually choose to do is write my mode decomposition this way, so that the a's and b's obey the usual harmonic oscillator algebra. So that A with A dagger is a delta function, and so is B with B dagger. Good. Now, the Hilbert space, again, will be a Fock space built up out of these. So you'll now have two different species of particle, one which is created by the raising operator A dagger, the other which is created by the raising operator B dagger, and we have names for those particles. We'll call them electrons and positrons. So the operator A dagger creates an electron with momentum p, and the operator B dagger creates a positron. And you can see it's not hard to see explicitly, given the way that phi and phi bar transform under these gauge transformations, that the particles E and the electron and the positron particles will have equal and opposite charge. And so, I mean, this is really a quite general principle, which is that whenever you have a complex scalar field and you try and couple it to electromagnetism and you quantize it, you always end up with particles and antiparticles. So the positron field, of course, is the antiparticle field of the electron, which has equal mass and opposite charge. You can immediately see that these have opposite charge here, because in this equation here, for example, the this equation contains an AP and a BP dagger. So that means that if AP increases the charge by 1, so removing an electron increases the charge by 1, then BP dagger adding a positron also increases the charge by 1. So that the electrons and the positrons must have opposite charge. And phi then, so if phi was a real scalar field, then phi is interpreted as the operator that either creates a particle or destroys a particle. For a complex scalar field, we interpret phi as the operator that either creates an electron or destroys a positron. Phi bar, of course, being the operator that either creates a positron or destroys an electron. And the really interesting thing is that the interactions of the electrons and the positrons are highly constrained. So, in particular, the fact that our action is real implies that the interactions, or rather it constrains the possible interactions of fields with the electrons and the positrons. So, for example, our coupling, so let's say that we wanted to couple, have this electron and positron interact with some other uncharged particle, let's call it chi, then the only way that you could do so, and your action would remain real, would be to have an interaction of the form chi times the absolute value of phi squared, or chi phi bar. And this would be an interaction where you have a chi particle that would then come in and, say, emit a positron and an electron. So the reality of the action, that is to say the invariance of the action under this gauge symmetry where phi goes to phi to e to the I lambda, then guarantees that all of your interactions will conserve charge. So you can't create just a positron or an electron. They must be created in pairs. Okay. So the point is that since each term in the Lagrangian is invariant, the interactions will individually conserve charge. So not only is the whole Lagrangian invariant, the whole action invariant, so that charge is conserved, but because each individual term in the Lagrangian is invariant, all of the various vertices that you'll get when you write down Feynman diagrams will each individually conserve charge. So when you draw a Feynman diagram, you should be able to trace exactly how charge flows, and as charge flows through the vertices, charge should always be conserved. Just as when we constructed Feynman diagrams, each of the individual terms in the Lagrangian was translation invariant. Not just the whole Lagrangian, but each of the individual terms in Lagrangian is translation invariant. And that meant that momentum was conserved for each vertex in the Feynman diagram. And indeed, as you trace through the Feynman diagram, you could follow the flow of momentum and verify that momentum was conserved at each vertex. So this means, for example, that when we consider processes where virtual particles are produced, even for virtual particles, even though they're never observed, you'll always conserve charge. You'll always create only virtual electron-positron pairs. Good. Any other? Yes?
The phi field should create a positron, right? Not one.
Probably. Okay, thank you. Yeah, never was very good with signs. Yes, thank you. Good. Other questions? Okay. So that's the Hilbert space of the theory. Let's now talk about the interactions of the theory. So the first thing that we need to do, if we want to consider interactions, is construct the propagators. And the propagator for the fields phi and phi bar is going to be the same as that for the real scalar. So in this class so far, we've learned 3 different ways of deriving the form for the propagator. One way you could derive the form for the propagator is, well, let's say you want to construct the following propagator. So the propagator, which is the time-ordered product, say, of phi bar phi, or to write that out in a little bit more detail, the vacuum expectation value of the time-ordered product at phi of x1 and, or let's say phi bar at x1 and phi at x2. So I can think of at least 3 ways of computing this. One way would be to take the Fock space decomposition of this and insert this in here, and just you get some quantity that's quadratic in the raising and lowering operators. You do a bunch of commuting things through, and you end up with an integral expression for the propagator. Another way would be to use a path integral. So, for example, well, as we saw with the real scalar field, in a free theory, the path integral is just a Gaussian integral, which you can compute. And of course, the third way of computing a propagator is just to notice that the propagator is the Green's function for the wave equation. So the propagator is the quantity that when you act on it with the wave operator, you get a delta function. Okay. And the simplest way to see that this propagator is going to be the same thing as it was in a real scalar field theory is to note that the equation of motion is the same as it was in a real scalar field theory. So that means this is just going to be given by the usual expression, which, if we wanted to, we could write in momentum space as 1, or I, that's just a convention, over k squared minus m squared, with the I epsilon, again, to ensure that when we compute this explicitly by doing the k integral, we get the proper terms when we do the k0 contour integral. By the way, you might be asking, what about, say, the 2-point function of phi phi, or phi bar phi bar? What about that? Let's see if you're paying it. Can anyone tell me what that is? So phi is an operator that creates, what is it? Phi creates an electron or destroys, sorry, it creates a positron or destroys an electron. No matter what it does, it increases the charge of your state by 1. So that if you take phi of x, phi of y acting on the vacuum, you end up with a state with charge 2. The vacuum has no charge, so this guy has to be equal to 0. The only reason you got something non-zero here is that you had a phi which increased the charge by 1 and a phi bar which decreased the charge by 1. Okay. That's why I wrote a phi bar phi expectation value there. So you can immediately see here that any correlation function with a different number, say with n phis and m phi bars, is going to be equal to 0 unless n is equal to m, and that's just by conservation of charge. And that's something that'll be just as true in an interacting field theory as it will be in this free field theory. The reason being, of course, that all of your interactions individually conserve charge. Any process with, say, n units of charge going in at the beginning has to have n units of charge at the end of the day. There's only one slight complication of this theory as compared to the real scalar field theory, which is that there are, technically speaking, 2 different propagators that we need to keep track of. There's the one which is the expectation value of phi bar phi, and the expectation value of phi times phi bar. Now, those are going to be complex conjugates of one another, but it does mean that we need, when we write down a Feynman diagram, say in position space, we need to have some sort of notation that we use to keep track of which one is the phi and which one is the phi bar. Okay. So we usually have a little arrow that we use to mark up a Feynman diagram to indicate which direction the charge is flowing. Okay. So in particular, if we have a phi bar here and a phi over there, then the arrow indicates which way the charge is flowing. And of course, this would be the complex conjugate of the Feynman diagram with the arrow oriented the opposite way. So this is going to be a general strategy when we, or a general phenomenon. When we considered real scalar fields, all we needed to do was keep track of the momentum that was flowing along these Feynman diagrams. When you have other sorts of particles which have more quantum numbers, that is to say more conserved quantities associated with them than momentum, we're going to need to mark up our Feynman diagrams to keep track of this. Okay. We have a particle that carries charge, so we need to have some additional notation on our Feynman diagram to indicate which way charge is flowing, just like we had momenta that indicated how momenta was flowing. And when we have photons, we'll also need to have some additional notation that will keep track of polarizations. Actually, for photons, it's not going to be so hard. Any questions before I continue? Good. Okay. Now, the photon propagator is going to be a little bit more complicated. So in particular, what we're interested in doing is computing the time-ordered vacuum expectation value of A mu of x, A nu of y. And typically, we're going to be interested in writing this in momentum space rather than in position space, because we'll be interested in scattering processes. And so I'll write the momentum space propagator as pi mu nu. Note that because each of the photons has an index, pi mu nu is going to be some sort of symmetric tensor, a 4x4 matrix worth of propagators. Again, I can think of three different ways of computing this. We could either insert our expressions for the expansion of A in terms of raising and lowering operators and compute this explicitly. We could work it out in terms of a path integral by doing a Gaussian integral. Or we could just look for the quantity which solves the equations of motion, which is the Green's function for the equations of motion. Of course, all of these will give you the same answer, but in each case, the answer for pi mu nu will be gauge dependent. And that's to be expected. A mu is gauge dependent. It changes under gauge transformations. So pi mu will as well. But the important point is that the answer for any physical process will not be gauge dependent. So in practice, what we're going to do is we're going to use a gauge where the form for pi is as simple as possible. And as long as we are consistent in our gauge choice, the answer will be independent of our choice of gauge. So, for example, we could work in Coulomb gauge, which would give us one particular form of the propagator pi. And as long as we're careful to continue to use that Coulomb gauge form for pi in all of our calculation, then your answer will, at the end of the day, be the same as if you worked in some other gauge. So what we're going to do is just find some expression for pi that is going to depend on our gauge, and we'll just choose a gauge to make our life simple. Let's see, I've got 7 minutes left. I think it might take me more than 7 minutes to work out our expression for pi, the photon propagator. So let me pause here and see if there are any questions. Should I do it? Let's see. It will take me more than 7 minutes. Okay. Maybe what I'll do is I'll release you 7 minutes early. This is a great time for questions, comments. Okay. Rather than trying to squeeze the photon propagator into the last 7 minutes, maybe we'll just stop here and we'll pick this up again on Thursday, where we'll finish our derivation of the Feynman rules for scalar QED. Great. See you on Thursday.